Well, today we will learn the refrigerator. All of us have learned the Carnot's heat engine. The refrigerator is a household appliance that is used to keep our food products fresh. So it is clearly a Carnot's heat engine that works in the reverse order. All of us have learned the Carnot's engine. So a refrigerator is a Carnot's heat engine that works in the reverse order. We will see the block diagram of the refrigerator. We have a compressor, a cold food space, and the warm outside. The cold food space will be at a temperature T2, where heat Q2 is absorbed. Why am I giving the terms Q2 and T2? Because I told you it's the Carnot's engine that is working in the reverse order. So we have a work W being performed by the compressor on the refrigerant, which is a low boiling point liquid that is present inside the evaporator of the cold space, that is actually creating the cooling effect. So the heat of compression as well as the heat that is absorbed from the cold space is sent out to the warm outside, which is at a temperature T1. And the heat that is sent out, let us call it Q2. Now, if Q2 is the heat that is absorbed from the warm food or the food that is present in the cold space, and if W is the work that is done. Now remember, Q2 and W, they have the same units because the work done is nothing but has got the unit of energy. So Q2 plus W is equal to Q1. Now, looking into the diagram of a refrigerator, we have got, as I told you, an evaporator that is situated inside the cold food space, which will have fins. Now let me draw the fins as these small lines or projections on this coil which I have drawn inside the cold space. This is the cold, we call it the food space. I told you a heat Q2 is absorbed by the refrigerant that is present in the evaporator coil upon which these fins are present, and the cold food space is at temperature T2. Now what happens is that, let me complete this drawing. We have this compressor C upon which a work W is performed, and this is the radiator coil. Let me explain to you. Radiator coil that is present outside the refrigerator, and we have an expansion valve just before the evaporator coil. We will label it one by one: expansion valve, the condenser or radiator. Now what happens is that the refrigerant that is present inside the coil of this evaporator with fins is a low boiling point liquid. It absorbs the warmth of this food space. The food that is placed warm is made cool by air that is circulated in this space by means of a fan that is providing that air for circulation, and the air that moves in this cold food space will transfer the thermal energy, the heat energy, into the refrigerant that is present inside the coil through the fins. Or the fins, they provide extra heat transfer area. So the thermal energy is transferred into the refrigerant, and the refrigerant absorbs thermal energy, and that thermal energy is converted into chemical potential energy. Because of that, the refrigerant that absorbs its latent heat of evaporation will become a gas, and it moves into this compressor all by itself. In the compressor, work is performed where the gas is subjected to some sort of a constriction, and it then moves into this condenser at a high pressure, and because of this compression, there is heat of compression also generated. So there is high pressure as well as high temperature. Inside this condenser, which is situated outside the refrigerator, we have an insulation that is provided that separates the cold food space with the warm outside. So the heat of compression and the warmth that has been absorbed is sent out to the warm surroundings, which is at temperature T1. I told you that we give this suffix 2 and 1 because the Carnot's heat engine that works in the reverse order is the refrigerator. So now, after reaching the condenser or the radiator, I mean the external heat exchanger, there is heat transfer into the surrounding, and once there is heat transfer, there is a decrease in temperature. So this high pressure, high temperature liquid, I mean the gas, fluid, the high pressure fluid, the gas that reaches the expansion valve, the term itself is clear. The expansion valve quickly reduces the pressure once the fluid comes out of this. Because of that falling pressure, the temperature also reduces, and again it is converted into a low pressure, low temperature liquid, which continuously evaporates in this cold food space, absorbing its latent heat of evaporation. So this process repeats. In the process, this cold food space is cooled again and again, and thereby work is done by the compressor in moving the warmth from this cold food space into a region of high temperature, or the heat transfer is in such a way that the transfer is against the natural flow of heat from this cold food space to the warm outside. So to discuss the coefficient of performance, we call this alpha as the coefficient of performance, which is nothing but the heat absorbed from cold space divided by work done by the compressor on the refrigerant, which is equal to Q2 divided by W. Let us say that. Now, just at the beginning I told you that Q2 plus W will be, let me rewrite, alpha is equal to Q2 by W. I told you Q2 divided by, where W is nothing but Q2 plus W. I had told you that Q2 plus W is equal to Q1. So Q2 divided by, instead of W, I can write Q1 minus Q2, because I transfer Q2 onto the other side. So I get Q1 in place of W, Q1 minus Q2. Proportionally, I can write this as 1 divided by Q1 by Q2 minus 1, or in terms of temperature, 1 by T1 by T2 minus 1, nothing but equal to T2 divided by T1 minus T2 will be the coefficient of performance in terms of temperature.